All right, this is Mr. Holsey with 8 Squared Sufficiently Understood Science, and today we are going to be looking at balanced and unbalanced forces. So, a good question to have is, what does motion have to do with forces? Now, you'll be surprised how closely these two concepts actually go together. So suppose we are in class and I asked you to move a heavy desk in the classroom. How would you move it? Well, you could get on one side and start pushing. You could grab the legs and start pulling. You could lift it. There's lots of different ways. But any way that you do it, you're going to be using force. So a force is a push or a pull that creates a change in motion of objects. So anytime you see something moving, you can be sure that a force has created its motion. Even when something is someone's walking across the floor, they are using force to create that motion. Now these forces are everywhere. Without forces, sports, dancing, driving, basically everything in the world would be impossible. That includes breathing, because your muscles use force in order to move things around in your body. So some forces, like weight, are present when things are not moving. So weight is a force. I know you go to the doctor and they say you weigh X number of pounds, but you actually don't have, let's say you weigh 110 pounds. Okay, say you weigh 110 pounds. The thing is, you don't have 110 pounds of matter inside of you. Weight is actually measured not in pounds, but newtons. So if I wanted to know how much actual matter something has, I would simply take that 110 newtons and divide it by 9.8 meters per second squared. Gravity. I do it by gravity. So 110 divided by 9.8 will give us 11.22 pounds of all the matter that is you. Of all the matter that is you, that is it. You have 11.28 pounds of matter. So if we put you in the vacuum of space, all that is you is 11.22 pounds. Now, because of this, I can easily calculate what your mass or what your weight would be on different celestial objects, because weight is a force. And so force is equal to mass times acceleration. Gravity is acceleration. So if I know the mass, I can determine what the weight is. So weight is equal to force, so W equals M. So if we did the formula, it'd be W equals mg. That's weight. So if I wanted to know what you weighed on, let's say, the moon, all I'd have to do is multiply that by the moon's gravity of 1.62 meters per second squared. And so if you were on the moon, your weight would be 18.17 newtons. Now there are different types of forces that you're going to deal with. First off, we have contact force, which is created between two touching objects, such as you holding a pencil or hugging someone. Then we have gravity, which on Earth is 9.8 meters per second squared. It's actually a form of acceleration. The force of attraction between two different objects. And all objects that have mass or have matter have gravity. So Earth's gravity pulls all objects, while you also have a gravitational pull that pulls objects towards you. Then you have friction, a force that resists movement between two surfaces that are pressed together. So gravity pulls this skater toward the ground. Pulls that skater towards the ground. The contact force, the skater is pushing backwards, and so an equal and opposite reaction happens and is propelling them forward. And friction is pushing, trying to stop the skater. Now this is all well and good, but there's another force that we have to think about. So if we look at this picture again, there is another force present, and it's holding the skater up, and this is called the normal force. It's a support force that exerts upon an object when it is in contact with another stable object. Another object, when we say stable, not in motion. So our units for force is the Newton. So 1 Newton is equal to accelerating a 1 kilogram object at 1 meter per second every second. And so 1 Newton is equal to 1 kilogram times meter per second squared. If we go back to the force formula, force equals mass times acceleration. So if we look right here, here is mass times acceleration. Now, forces have magnitude and direction. Okay, so it's like velocity. This force is called a vector. And so that means it has a size or magnitude and a direction. So we have a kid right here kicking a ball, right? So when he gives a small force, the arrow is very small. When he gives a big force, the arrow is bigger, because the amount of strength of the force increases. The amount of strength of that force increases. So this is going to be measured in newtons because it is a force. So a vector is an arrow used to show the direction and size of a force. So the larger the force, you'll get either a short arrow or a long arrow. Sometimes instead of a long arrow, you'll get one that is thicker, not longer. But basically, it's showing you visually the amount of force and direction of that force. So the arrow points in the direction of the force, and the length or thickness of the arrow represents the size or magnitude of the force. So some very simple examples. A small force of 500 newtons would have a very skinny arrow, very small force. Whereas a large force of 500 newtons would have either a long or a very thick arrow. And yes, this is a real thing. This is the Shockwave jet truck. Travels at 376 miles per hour. So usually, though, more than one force is exerted on an object at the same time. And so we add all those forces up, we put them all together. The sum of all forces acting on an object is known as the net force. Okay? So you need to look at the net force in order to figure out if or how an object will move. So we have examples such as balanced forces. Now, a balanced force has a net force of 0, meaning that there's not going to be any change of motion. So 3 examples that we could use is a piece of paper on your desk, you sitting in a chair, or a flag not moving. None of these are moving at all. They have 0 net force. No force, everything. But that doesn't mean that there aren't forces acting upon the object, because there are. Gravity is still there, everything like that. It just means that all the forces combine together cancel each other out and make it 0. An unbalanced force, such as right here, is where there's a net force acting on the object, causing a change in motion. Now, it's possible to add forces together and find the size and direction of that net force. So if it's acting in the same direction or acting in the opposite direction, we can figure out just how unbalanced that force is and get an idea of the direction an object is going to move or how strongly an object will move in that direction. So if the forces are moving in the same direction, we add those forces together. So for example, we have a girl pushing at 25 newtons to the right, a boy pulling at 20 newtons to the right. So these are heading in the same direction, which means we're going to add those forces together. They're working collaboratively, they're working together. And so the net force is going to be 45 newtons to the right. Now, it's important in net force equations that you give the direction. If it is an unbalanced net force, you must give a direction. If you don't, it is wrong. You must give the unit and the direction. Here's another example. So the forces are now moving in opposite directions. One's moving to the left, one's moving to the right. We're going to subtract them. Now, you will never end up with negative net force. Okay? 0, positive, and up. Okay? So you'll just subtract the larger number, or have the larger number be subtracted by the smaller number. So dog number 1, right here, this is dog number 1, is pulling with 10 newtons to the left, and dog number 2 is pulling with 12 newtons to the right. And so 12 minus 10 newtons will give us 2 newtons. Now, because this dog is pulling with more force, 12 is bigger than 2, this side is going to have more, the net force, the 2 newtons, will be to the right. Okay, so net force, 2 newtons to the right. This is an example of a more difficult net force equation. So here, instead of 2 forces, we're dealing with 4. So 4 forces are acting on a box as shown below. 40 newtons downward, 20 newtons to the right, 10 newtons upward, and 30 newtons to the left. So we're going to look at how these are acting against one another. So we have 10, let's start with going up and down. So we have 40 newtons downward, 10 newtons upward. So 40 minus 10 will give us 30 newtons. Now the stronger force was downward, so 30 newtons down. Now let's look at the left and right. So we have, I did plus, I don't know why I put it there. Anyway, so we have 30 newtons minus 20 newtons will give us 10 newtons. And in this case, it'll be going to the left because this arrow is going to the left. It's the stronger force. And so the box will be increasing in speed. The box is still increasing in speed, but because of these forces, let me go ahead and erase this right here. Okay, we have a force going down of 30 newtons and a force coming here of 10 newtons after everything cancels out. And so this object will be going in a slight diagonal. Now it won't be uniform. It won't be a perfect diagonal. Okay, it'll be actually going a little bit more like this, more down than to the left. because our force going down of 30 newtons is stronger than our force of 10 newtons. And so the box will increase in speed downward to the left. So we're going to do one more example, and I want to see 2 through 6 here in the comments below. So we have 15 newtons going to the right and 20 newtons going to the left. So we'll subtract these numbers and we'll end up with 10 newtons because they're going in opposite directions. If they're going in the same direction, like number 4, here's a little hint, you would add those together. But we're going to have 10 newtons, and because 25 is the stronger of the two forces, 25 newtons was going into the left. Therefore, our answer is 10 newtons to the left. So I hope you enjoyed this tutorial on balanced and unbalanced forces. Don't forget to like, share, and subscribe so you can always be updated when we post new tutorials. This has been Mr. Holsey with H Squared Sufficiently Understood Science.